Then I want to introduce one thing we briefly discussed. Then I say, well, we'll talk about that later. That's the DNA polymorphism within population. We can calculate the heterozygosity as an indicator for DNA polymorphism. We also can use the different estimates to look at the sequence level polymorphism. And now we want to introduce different methods to estimate the polymorphism level. Why I use estimate? Imagine there's a population with only 20 individuals, and you can easily sequence the 20 individuals for a certain locus and tell me what's the polymorphism level. You say, okay, they are 7 segregating sites at a frequency of ... So you can describe it. And that's the true polymorphism level of the population. However, in most cases, actually in all the cases, we don't exactly know all the numbers from the population. We cannot really sample every single individual from natural. So usually we are taking a sample of a population to estimate the polymorphism level. But as I just mentioned, the polymorphism level is a fact in the population. We're just unable to calculate it. So we have to use our sample to estimate the polymorphism level. And we can use different ways to estimate the polymorphism level. And if the truth is one fact, then the different estimate, if all the different estimates are unbiased, then they should be the same. So that's the basic idea about the polymorphism. Okay, so this is just to illustrate the changes in the population. So the red dots are the mutations in the population, then they evolve, then they become like from fewer variation to higher variation. And evolution, all the evolution forces will shape the polymorphism level in the population. If we are doing a sampling of this and using the occurrence, so this is the idea. So the occurrence, if we only have a few number of sequences, and we can count the occurrence for each category. So this mutation, this derived mutation happened once, twice, 3 times, or 5 times. And that's the idea of counting the site variation and construct the site frequency spectrum. Under neutral evolution, the estimate, I changed the K to S. The estimate to the what we call segregating sites. Segregating sites is the sites showing variation, showing polymorphism in our sample. Those are the segregating sites. So the segregating site is in a relationship with the population polymorphism. We use the theta as the estimate. So that's the theta here. And I say in the proportion in time a parameter. And that parameter is 1 plus half plus like third and fourth and 2, like number of sites minus 1, number of samples minus 1. So this is a sampling idea. So that's a simulation. So this is equivalent to the gray bar in the review paper. That's a neutral mutation. So under neutral hypothesis, when you survey the segregating sites in the population, a lot of category mutations will occur in the lower frequency. And toward to the high frequency, the segregating sites become fewer and fewer. So that's the neutral expectation. And that's the frequency spectrum for that. So if we want to estimate theta. So that's the polymorphism we are going to calculate. And based on the segregating site, and that's the formula we put it here. So the expected number of segregating sites, S, is the theta, the DNA polymorphism, the nucleotide polymorphism, times A. Then A is the parameter listed here. So that means we can use the number of segregating sites divided by A to estimate theta. So you put A under as the denominator for the estimation of the segregating site. Then you can estimate the theta. And Watterson is the one to first propose the polymorphism, the relationship between the segregating site and the DNA polymorphism. That's why we also call this the theta W. W stands for the initial of the Watterson. So that's the formula. So that's one way of estimating the polymorphism in the population. Remember, in chapter 2, we talk about theta equal to 4n mu if it's all contributed by neutral variation. So n is the population size, mu is the mutation rate. And here is the same idea, but we use the segregating sites, number of segregating sites S, to estimate the theta, and we call it the theta W.